Okay, ladies and gentlemen, one more quick video to just tie up or introduce the beginnings of the next topic, right? Because now we've talked about the properties of waves, the 10 or so that was on that list, the small formulas that come along with waves and how waves operate, they interfere, right? They disperse. Now the question is, okay, what do we do with these electromagnetic waves? What are some of the conclusions that we can make about them, right? If we have an electromagnetic wave shining on something, what can it do? How does it interact with that surface? And how does it lead to some practical applications that we know and love in the world around us? Like, these things that are on my head, right? You could even see it when I do this in a camera, right? That the way the light comes in towards my eyes changes because, as the light comes, well, it bounces off the surface, it goes through these things, and they change the direction of the light. Well, how does it do that? These are the types of questions that we want to be able to ask and be able to make some sense out of all this stuff. And as it turns out, it's really not so bad. It's fairly quite intuitive. And so I want to jump in today's video into just what some of those principles are, what some of those basics are, what some of the jargon is there, and then we'll expand upon that next time with some problem solving. So let's go for it. So this is the general topic, like we said, of basic optics, or some people will even put an extra word on this and call this geometric or ray optics, right? And what it basically says is, and this is my glorious picture of a light bulb that is shining light out from it. And what do we know? We know that when light leaves a light bulb, it goes out in all possible directions. Okay, which directions do we care about? It's typically only the direction that has the thing that we're going to look at, the effect of it or something like this, right? But what do we know? The light leaves that bulb and travels in all directions, and it moves through air at the speed of light, which I remind you, c 3 times 10 to the 8th meters per second squared, right? Yes, the speed of light in air is slightly different than the speed of light in pure vacuum, but for our purposes, vacuum and air are going to operate the same way, and all the problems that we're going to be talking about in this context happen here on the Earth, which, I mean, we can't do experiments. Well, we can, but it'd be a bad idea for us to do experiments in a place where there's no air. So yeah, what we're going to be doing is that the vacuum speed is going to be the same as the air speed, okay? But that doesn't mean that the speed of light, although it's constant, although we believe that that speed of light is the same for all reference frames, all observers, the piece that we need to make sure that we understand there is that it's the speed of light in vacuum or in air that we all agree on. The speed of light is allowed to change if it goes through other media. If you've ever went swimming in your life, you have seen this, right? Things look different underwater than they do above water, right? Even you looking down into the water versus going into the water and looking up, the views look quite different. Well, why is that? Because the light rays, right, when you are looking down through the water, go in and travel in a slightly different path. You looking up, the same thing happens, right? You're seeing a distorted view, and then of course the fact that water has waves doesn't help the idea. But you've even seen this happen in still water, right? If you've ever put a pencil in a glass of water, then you've seen this effect, right? It looks like the pencil is bent. Try it for yourself, right? Well, why is this? It's because the speed of light that's bouncing off of that pencil to your eye is slightly different with the piece that's sticking out in vacuum and slightly different with the piece that's stuck in the water, right? So we say the speed of light is different in these two medias, right? And remember, we said waves need a media to travel, okay? So we're going to give a name to this, okay? We're going to give a name to this concept. We're going to call this the index of refraction, okay? And so what the index of refraction is, it's going to be a ratio of the speed of light in vacuum to the speed of light in the actual surface that we're talking about, such that those two numbers are the same, obviously, for air. So the index of refraction, which we're calling lowercase n, is equal to 1 for air, okay? Typically speaking, then all the other indices of refraction that we're going to have will typically be greater than 1, right? Meaning that it's going to move slower outside of the it's going to move slower in something that is not air, okay? And so what can happen? Here's our simple ray diagram. We have a light bulb on the ceiling, and let's say that we wanted to see what happens at this point, which I then put on an origin, and let's say that it happens at some surface, right? So The light bulb is in air, it has some index of refraction n1, and then it hits some surface. Let's say it's a surface of glass, like my glasses, or the surface of a bed of water, which then has some different index of refraction n2. What are the only possible things that can happen to this light? Well, some of that light we know comes in and gets bounced off of the surface. It gets reflected, okay? Well, which way is it going to get reflected? What's the relationship between the incident angle versus the reflected angle? But what else is it going to do? Some of that light is going to transmit through the water or the glasses, right? And we just said that since the speed of light is different in two different media, that light, when we look at it from an external perspective, is going to be bent. Okay, and so we can calculate what that angle is that we call theta 2 there, which we would call the angle of refraction. Refraction is for us to go through the material and into the next media. Reflection, drawn there in red, is you bouncing off of the surface of the media and sticking into the same media or the same index of refraction that we started with. Okay, and the two big takeaway formulas that we need to do here, right, is the first one should be very intuitive, right? That the angle that the light comes in, and if it bounces off of a surface, better equal to that same angle. Conservation of momentum, if you will. Okay, there's a whole other can of worms behind that because now I'm equating light to act like a massive particle, and we can dissect all that. But for today's purposes, it should be intuitive, right? That the angle that something is incident, if it is to bounce off, right, bounces off at that same angle. Notice how we drew it though, right? This is just the way that we typically draw angles in optics. We typically draw them, right? We usually measure from 0 and go up. When we do it in optics, we typically draw them with respect to a vertical, right? Because lights typically come from the top. And so just keep an eye as to when you draw these as to where the angles actually are, because what I call theta incident there, notice it's the angle to the vertical as to where the light comes in, and theta reflected, again, is the angle in here, right? Again, with respect to a vertical. Same thing happens with the other angle, right? Refraction, what I call theta 2 there, okay? And the law for refraction is this thing called Snell's Law, which is, well, we're not going to derive it because, again, this is not a calculus-based class. It's a really interesting calculation to get that formula to pop out. But basically, if you just assume that light always travels the shortest distance between 2 points, and you evaluate a bunch of length segments between where it started and where it ultimately winds up, you can get to this conclusion on your own using the law of sines and other things, which is why it has this form down here. But we call this Snell's Law. And what it basically says is that the index of refraction times the sine of the incident angle is equal to the index of refraction of the new medium times the sine of that angle of refraction. Again, where everything is measured with respect to the vertical. And so with these two equations, we're able to figure out what trajectory light has when it's incident on a surface, right? Will it bounce or will it transmit through? And by the way, sometimes you might have numerous surfaces. If we put another surface in there, if it bounced off of that surface, well, again, theta incident would have to be equal to theta reflected. And if it transmitted into that third surface, theta n1 or n of that object, sine of theta of that incident has to be equal to the n of the third object times the sine of the theta of its object. So these carry through all the way throughout. And they really are as straightforward as we made them sound, which is a nice lull compared to all the different problem solving that we've been doing recently with things like optics and with things like circuits and magnetics and stuff like this. So this is a really good place for us to be at because it gives us a really nice reprieve. And again, it has a really nice practical application that we'll be able to wrap our heads around. So the big takeaways here for this video, right, is thinking about when light is incident on a surface, what can happen? It can either bounce off or it can transmit through. If it transmits through, the speed of light will be in a new medium, so therefore it's going to be slightly shifted between that in air and that within that medium. If we know that, we then know how to calculate the paths that it takes based on if we know its incidence, we can know it's reflected. And if we know information about the indices of refraction, then we can figure out what those refracted angles are. For different materials, all of those indices of refraction are given in your textbook, or you can look them up online, unless, of course, the problem wants you to find the index of refraction, in which case then that's just part of the problem. But otherwise, it's just a number that's a material property, just like how dielectrics were and coefficients of kinetic friction and static friction, right? They're things that we look up and can use. And so, again, we want to wrap our heads around the idea that these are the two options that we have available to us, reflection and refraction, and we now have a mechanism for getting the trajectories from those. And so next time when we come back, we'll do lots of problems involving just drawing these lines and using these simple concepts and seeing how deep we can take that and how much understanding we can actually get out of it. As always, ladies and gentlemen, if you have questions, comments, complaints, or concerns, please don't hesitate to ask them. I hope I was able to shed some light on this subject. Aren't you so glad you made it all the way to the end of the video just to hear that one joke? Until then, ladies and gentlemen, I miss you all, and I hope you have a fantastic day.